In this next example, this is our last one, we're going to write the function for this. So our function that represents this integral that we can integrate, is y equals e to the x over 1 plus e to the 2x. So we're going to set up the limit. The area is equal to the limit as a approaches infinity from 1 to a, and this is going to be e to the x over 1 plus e to the 2x dx. So again, this one cannot be integrated, so we're going to use a substitution. And in this case here, because if we choose 1 plus e to the 2x as our u, we're going to run into a bit of a problem in that we're going to end up with the derivative not matching the outside function. So the way around this is we need to recognize that we're actually dealing with a 1 plus x squared in the denominator. And I'll show you how that works. So we're going to let the u equal e to the x. And then that makes our du equal e to the x dx. Well, that's great because I have now my outside here is represented by du. And now when I express the new integral, you're going to recognize that this is actually an arctan integral. So it looks like this. Limit as a approaches infinity, x equals 1 to x equals a. Now the du is going to replace the e to the x dx. So I'm just going to put that in. So that replaces the blue highlighted part. In the denominator, I have 1 plus e to the x squared, which is the same as e to the 2x. And that e to the x squared then, this is going to be, I'm going to replace the e to the x with a u. And so we end up with 1 plus u squared. And this is an arctan integral. Okay, so the way I've done the substitution generates a form that I can apply arctan to. So then we end up with the limit as a approaches infinity. This is going to be arctan of u. And the bounds of integration are going to be from x equals 1 to x equals a, since we're still in terms of u. When I do the next step, I'm going to replace the u with the e to the x, so I get limit as a approaches infinity, arctan, and this becomes e to the x. And our bounds now are in terms of x's, so I just write them as 1 to a. Doing the substitution, I end up with the limit as a approaches infinity, the arctan of a minus the arctan of e to the 1. Okay, so then I'm going to plug my infinity into this expression, so I end up with arctan infinity minus arctan of e. Well, arctan of infinity, well, the tan is the slope, so the infinity represents slope. So what angle gives us an infinite slope or a vertical slope? That angle must be pi over 2. Now we're going to subtract arctan e. I can just leave it like this because I know that arctan e is a finite value, so we know that this must be finite. If you're not sure about that, we could always just plug arctan e into our calculator. And plugging arctan e, we end up with the pi over 2 minus the angle, arctan E works out to be 1.218. So again, it still leads us to the conclusion that that's finite. So if the integral is finite, we know that the series is also finite. So from 1 to infinity of e to the n over 1 plus e to the 2n is convergent. Okay, so that's our conclusion for example 8. Now, it's important to recognize that this test is a bit limited in that we need to have a expression in the an, which is in this part here, the expression. We need that expression to be able to be integrated, and that's not always going to be the case when we do series expressions or series expansions like this. So it does have some limited use, although if we can use it, this is a valid way to use it. And by connecting the integral or the area under the curve to the series, the discrete series sums, which although they're not the same, one does relate to the other.